Okay, so we're dealing with cyclic groups, so just by way of reminder. Is cyclic if it's generated by a single element. That is, if G is that which we learned was the set of all A to the K, such that K is an integer. All integer powers of K now if it's finite, if the group is finite, this wraps around, so there's only a finite number of elements, as we'll see. And we left off with something on the board. I just want to summarize the first part of the proof. And then I want to talk about why this idea is so helpful and useful. So we had this condition, and suppose the order of G is n. That means that G to the n, and I'll adopt the book's notation for now that 1 is the identity, just so it'll be compatible with the reading. I prefer E because it's a more general identity, but we'll call that thing 1. And we had the following, that G to the K, some other integer, is 1 if and only if K is a multiple of n. And the proof went as follows. Suppose that n divides K. That means that K is some multiple of n. I'll call it Ln. And because this is integer, these are integer exponents, these are integers, this is clearly the same as NL, right? Integer multiplication commutes. Then we have G to the K is equal to G to the NL, which means I have L copies of G to the N, which is really G to the N to the L, but G to the N was by definition, because the order of G is 1, it's 1. So we have the forward way, the backward way. If n divides k, I certainly get 1 for the answer because I'm taking 1 raised to the power. And they go the other way. So we'd say this is that way of my if and only if. Assume this side and show that side. And going the other way, we assume, this was the more subtle one, that G to the K is 1. And then we write, using the fact that integer division always works. Remember, these exponents are integers. I can write K as some multiple of n plus a remainder where the remainder is strictly less than n. Because if the remainder was n, I could increment L by 1, right? I keep going until I get a remainder that's smaller than my divisor. That's the division algorithm. Then what do we have? Then we have that G to the K is equal to G to the Ln plus, Ln plus R in the exponent. But remember, adding exponents is multiplication, so this is actually G to the Ln times G to the R. But now let's look at what we have here. We assume that G to the K was 1. So this is 1. And what's G to the Ln? 1. So I found a number smaller than n, raised to that power, I get the identity. That's a contradiction of the fact that the order is n. The order of that g is n means that's the smallest one that does that. That's a contradiction. Unless r is 1, 0. That's allowed, a remainder of 0. That's legal because anything to the 0 power is automatically 1. But that's the only legal one, because otherwise it would contradict the fact that the order of g is n, which is bigger. So if r is 0, then we get that k must be ln, which means that n divides k, and that's my other direction. So that's what we have. And we're going to continue with this idea, with this theorem in parts of it. But I want to step back for a minute and look at how this stuff works, why cyclic is so important, and how we apply it. So one of the motivations for caring about whether a group is cyclic or not, or a subgroup, has to do with maps, operation-preserving maps that we'll study starting next week in detail. Suppose I have some map from a group to itself with the following property. That's an operation-preserving map, because it doesn't matter whether I operate on the elements first and then apply the function, or apply the function to the two elements and then do the operation. Now, you've seen these kind of maps before, right? A linear transformation of vector spaces has two basic properties. There's an operation-preserving map where the operation is plus, and we saw before that a vector space is a group under this operation, adding vectors. Okay, so now suppose that G is cyclic. So that's an example of an operation-preserving map. Then by definition, G is generated by one element, and that's the set of, we can write it this way, 1 comma G comma G squared comma G cubed comma whatever it goes, right? It may stop, it may loop around, but that's what the elements look like. They're all powers of G. So if X and Y are two elements in the group, how can I write them? That's the first. They're powers of G, right? So let's consider simply f of x well, this is an operation-preserving map. how can I write f as a product of two g to the k as a product of two elements? Well, certainly that's f of g times g to the k minus 1, right? But this math is special. It preserves the operation. So this is actually f of g times f of g to the k minus 1. But how can I write g to the k minus 1? I can write it as g times k minus 2. So if I continue pulling one g off at a time, it should be clear, and you could prove it by induction, that this is simply f of g to the kth power. Now, if I operate the two elements, what is x star y? Well, it's simply g to the k plus l, right? It's another integer power. So f applied to this is going to be f of g to the k plus l power, right? So every answer, this is the bottom line, in this case, if I know f of g, I know f of x for all x in my cyclic group, right? Even if it's infinite, because they're just powers of, right? F of x is just f of g raised to the kth power, if x is g to the k. By the fact that this is a special operation preserving math, it turns out there's a lot of them around. We use this in linear algebra. Right? If we know what a linear transformation does to the basis vectors, then we know what it does to everything, because I can write everything in terms of the basis vectors. Well, this is a generalization of that idea. When I have an operation preserving map and a cyclic group, if I know what this map does to the generator, I know what it does to everything. And so that's powerful, especially where the group is infinite. So I have a mechanism for computing f of any element if I know just the one answer, f of g to the k. So that's a motivation that we'll dig into heavily when we study things called homomorphisms and isomorphisms. That's what they are, is operation preserving maps between groups. Okay. Let's look at an example that puts some, hopefully, concreteness under these ideas, and it'll also help us start looking at properties of cyclic groups. It turns out that all cyclic groups of the same size are really the same group. So I'm going to let, suppose I'm in some group and the order of G is 12. Make it specific. Then I'm going to label this thing C12 is the group generated by G. What are the elements in there? Easy. 1, G, G squared, comma, dot, dot, dot. What's the last element? G11, right? Because G to the 12 is the identity. Right? So that's what's in the group. So I want to start looking at subgroups. Well, we generate subgroups by taking an element. So let's see what happens if I use all the elements of powers of G, so I can pick one of those this way. Let's look at G squared. The subgroup of the cyclic group of order 12, that's what this is called, cyclic group of order 12, generated by G squared. Well, what does that mean? What's definitely in there? Let's not start there. What's definitely in there? G squared. And then what else? G to the fourth, right? And then the product of those two, G to the sixth. And then the product of G squared and G to the sixth is G to the eighth. And then the product of G squared and G to the eighth is G to the 10th. And of course, G to the eighth is also G to the fourth times G to the fourth. Right? And then, what's the other element?
1.
G to the 12th, which is the identity. So we're done, right? And if I multiply any two of these, G to the fourth times G to the sixth is G to the 10th. G to the sixth times G to the 10th would be
4.
Yeah, because G to the 12th is 1, so this is G to the 4th, right? So you should be able to see that this is a subgroup. Because it's closed, has identity. What's the inverse of G to the 6th, for example? Well, I multiply G to the 6th by, I get 1. G to the 6th. So this is its own inverse. How about the inverse of G squared? G to the 10th. And this is easy. This is revealing something else. I'm doing this. I don't know what this group is. I don't know what G is. It could be a permutation or something, or a matrix. But all I'm doing is integer arithmetic, which is easy. So this cyclic idea turns hard group problems into integer arithmetic problems. So that's one motivation.
How did you know that it was closed? Just by looking at it.
Do the math. I actually did them all, right? You have to test them all. But 4 times 6 is 12. That's 1. No, it isn't. That's 10. That's that one. G8 times G8 is G16, but G16 is
4.
G to the 4th, right? So you have to actually see it, but it is. All right, what's the next element we can pick? How about G cubed? Well, what's in there? This should be easy. I just keep adding 3, right? So G third times third is 6. G9, and then what's next? 1. G12, G to the 12th power is 1. That's also a subgroup. What's the inverse of G to the 6th here? It's still G to the 6th, right? How about the inverse of G to the 9th? G to the 3rd. So these two are inverses of each other. G to the 9th times G to the 9th is G to the 18th minus 12 is G to the 6th, right? So it's closed again, has identity and inverses. Well, this is working pretty well. Let's see what I can get if I generate with G to the 4th. And by the way, since these groups are generated by a single element, right? G squared is a single element. These are all cyclic as well. So G4, we just keep going up the ladder. If I start with G4, I get G to the 4th. What's the next element? G to the 8th. And the next element?
1.
1, because it's G to the 12th again, right? And what's G to the 8th times G to the 8th? G to the 16th, which is G to the 4th. Right? So I'm really doing modular arithmetic on the exponents with a simple doing arithmetic mod 12 on the exponents. Okay, let's try one more. G to the 5th. Well, I have G to the 5th, of course. The next one would be G to the 10th. What would be the next one? G to the 15th, which is
3.
third, G to the 3rd. Right? And then I add 5 again, so that's G to the 8th. And I add 5 again. 8 and 5 is 13, which is 1. I could stop here. Now I've got G in here, right? What does that mean?
Not everything.
I'm going to get everything. But let's work it out anyway. If I multiply by G to the 5th again, I get G to the 6th. and then G to the 11th, and then 11 and 5 is 16, which is 4. And then 4 and 5 is 9. And then 9 and 5 is 14, which is 2. And then 7. And then 1, right? 7 and 5 is 12. That's the whole thing, right? So attempting to use G5 to generate a subgroup, I got the whole thing, so that's not a subgroup, that's the whole group. Let's do one more. Well, I definitely have G to the 6th. 6 and 6 is 12. I'm done. All right, let's try one more.
So once you see G all by itself, like how we had G to the 5th when we're working that out, we can automatically assume that we're just going to get the
Right,
group.
because if I start here, so I know it's in there. I know everything's in there.
So we can just automatically assume that it's a group. We don't
Yes.
even have to prove that it's a sub.
Correct.
Got it.
That's a nice shortcut. All right, one more then. And these are all cyclic subgroups. So I'll use this space right here. Let's try G to the 7th as my generator. And actually, I can really take shorthand here, right? All I care about is the exponents. 7 and 7 is 14, which is 2. Plus 7 is 9. Plus 7 is 16, which is 4. 7 and 4 is 11, which is 11. Plus 7 is 18, which is 6. Right? Plus 7 is 13, which is 1. So I have the whole thing. Right? 1 plus 7 is 8. Plus 7 is 15, which is 3. Plus 7 is 10. Plus 7 is 17, which is 5. Right? And then 5 and 7 is 1. Right?
So we have the group again.
So you get the whole group again, right? And we knew that when we get to here.
When is the last one if you read it like that in 0?
That's 10, right?
No, yeah, but you have G to the
Oh yeah, but yeah, 0 power is 1. Yes, thank you. As an integer exponent, 0. Okay. What do you suppose? Can you see a pattern here? When do I get a subgroup? Yeah, excellent observation. When the exponent is a divisor of this, right? This has to do with years. One reason these are called cyclic groups. If this guy has 17th and that guy has 11th and they mesh here, we're going to go around the product of the number of times before the dots line up again, because they're relatively prime. But if this guy has 14th and this guy has 12th, every time this guy goes around 3 times, that guy will go around once. Right? So they match. So I get a even thing going on here. So this is really sort of what's going on. And it's a theorem that we can write now. We get a couple of theorems. But before we write the theorem, I want to draw the picture. You should convince yourself that G to the 8th will generate the whole thing. G to the 9th, 10th, and 11th will all generate the whole thing. It will. So with this on the board, we can draw a subgroup lattice for this group. So we take C12 at the top. What's the 2 big subgroups? Well, the subgroup generated by G squared. That's got 6 elements, right? How about G3? Is this a subgroup of that one?
No.
No, because 9 is not in here, right? So that's not a subgroup, so that has to go directly here. The next smallest one is G4. G4 is a subgroup of what?
G
G2, is it also a subgroup of G3? No. So subgroup generated by G to the 4th sits there. And then G to the 6th, is it a subgroup of G2?
Yes. And
Is it a subgroup of G4?
No.
No, so it's a subgroup here. But it's also a subgroup of G3, right?
No.
Sure it is.
Yeah, it is.
6 and 1. And then what subgroup is a subgroup of these?
One.
Yeah, the identity, the trivial subgroup, right? So that's the lattice diagram for this group. And whenever you draw one of these for a cyclic group, the ones that work will always be divisors. In fact, if the power is a divisor